Okay, let's start. So, greetings of the day to those who will watch this on YouTube. Um, I welcome you all to this week 11 doubt clearing or problem solving session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma. I am a PMRF scholar at IIT Kanpur and I'm a TF for this course. So, last week we discussed. So we are currently discussing how uh, we are currently discussing demonstration of the systems that we have studied in this course. Today we'll continue with that demonstration aspect. And last year we talked about some power quality issues, coordinated voltage control schemes, micro operation of DC microgrids, and other stuff. Today we'll continue with our analysis of DC microgrid and we'll talk about simulation of AC/DC system, distribution system, and operation of um, smart DC microgrid in India. Okay, let me share my screen. Okay, so let's talk. Just a second. Okay, so we'll start with first the energy management of that happens in a DC microgrid. So we studied, right, power management and energy management. It's basically how you manage the flow of energy by supporting grid. It's mainly by employing management schemes to manage your load and generations, which inadvertently supports the grid as well. So, I mean, not inadvertently, we are managing our resources in such a way that we are able to support the grid needs, but also by employing these schemes, right? So this is a converter that we have been. This is the kind of DC microgrid structure that we have been seeing for the past few lectures, right? So we have a full H-bridge bidirectional converter. An H-bridge bidirectional converter is an isolated converter. So this is an isolated converter. An isolated converter is necessary because if we are connected directly to the grid, we need to ensure that something goes wrong with our converter, the fault doesn't proceed to the grid as well. So to protect our grid side, it's better. It's the use of an isolated converter is necessary. So our normal DC to DC converters, basic DC to DC converters such as buck boost, these are non-isolated. They don't have a transformer in between any of them. Here, the isolation is provided due to the use of a transformer, and that transformer acts as an isolation between the AC grid side and the DC bus. Right. So basic structure DC microgrid, we have a DC bus, and we have some PV panels which are connected to the boost converter. This helps ensure that we are able to employ our MPPT algorithms. We have a battery, we have an ultra capacitor to support the battery and the grid when during contingency issues. And we have some loads which are DC loads which are directly connected across the DC bus using relays. So this is the normal structure that we have been looking at for quite a while now, right? And the grid side, this converter is also called a grid side converter. So now the control scheme. So basically, why first of all let's discuss why even. So I have been quite vocal about this, but still to let everyone be on same page. Why are we discussing DC microgrids? It's because of their prevalence. So So DCMGs, so they are becoming more and more prevalent, right? So this is because of the growth of renewables. Second thing is that we have energy storage advancement. So we have now come to a point that EVs are there across the whole distribution, which can act as mobile storage, that they are movable storage, right? And then we have other lithium ion batteries, which have become now cheaper. I mean, um, um, uh, cheaper from what they were 10 years before, right? We are hoping if the trend continues, they will become more and more cheaper. And if they do become more and more cheaper, employment of these energy storage equipments with that of the renewable will help increase the renewable penetration altogether, right? So this is one more aspect to it. Then we have government initiatives. I mean, the government is planning for connecting more and more renewables across the whole infrastructure, right? These the solar rooftop schemes that our government has launched, and the other uh, um, government initiatives, they have called for better management by employing these DC microgrids. Yeah, apologies, someone came. So, yeah. So the government initiatives are one more aspect that are contributing to the the growing need or the prevalence of the DC microgrids. I mean, not only this, so we have one more aspect that there is less conversion. So we can supply our DC loads directly. So we don't need to have a conversion stage between them. So DC microgrids are helpful in that aspect as well. And the one more thing is that they are simple to control and have an efficient design because of less conversion state. Now, but we discuss everything good with it, right? But it won't be fair. We have to discuss what is wrong with this. What are some things that can hamper their growth? So, so some things hamper their growth. So one big thing is that we don't have necessary standard for them. So when I say necessary standard, is that IEEE has standard for AC distribution side. I mean, they have a fair amount of research has happened, right? So there are standards to support their widespread adoption, right? So lack of standards. So if we don't have standards, there won't be standardization or uniformity across the grid, right? Second is that their protection technologies are still being developed, and cost-effective and efficient um, protection techniques is a such thing that we lack. So these are some of the aspects that I wanted to discuss before moving on. So yeah. Now the control scheme, I mean, we have studied the same exact control scheme for too many times now, but still, just to have everyone in the same place. So we use the we want to keep track of our bus voltage. So we are in bus regulation mode, right? So we want our bus voltage to follow the reference bus voltage, which is fed to a PI controller and then to a low pass filter, which is then set to a rate limiter. The output of that is our current, which is fed to an inner control power flow control strategy. And this power flow control strategy controls the working of the inner control loops that control the battery, ultra capacitor, as well as the load, right? So let's talk about our power flow control strategy first. So a PFCS is basically uh, so used to account for optimal power flow cross network. So what we want is we want our the power flow to be in such a way that all our equipments work optimally, right? So this is one control technique. This is just a single control strategy. I mean, there are numerous strategies available online, but this is something that the instructor discussed that yeah. So this is something that the instructor discussed. We discussed one more control strategy last week as well, and it works on the similar line. I mean, if you want to control your components of your grid in certain way that can make them work in an optimal way, is something that you want to derive from that strategy, right? So let's discuss it briefly. I mean, I won't go into detail. It's pretty much self-explanatory, but still, some of the aspects that control this algorithm is something that I'm interested in taking. So the first thing, so as we can always see, our control strategy works in a flowchart design. So this is the starting point of this. So we first check if grid is available, or we can say that if the microgrid is working in a grid connected mode or in isolated mode, right? And let's say that it is working in a grid connected mode. Then we check if there is a PCAR. PCAR, so I'll explain here. Uh, PCAR is something that is a condition for the conventional grid. That is the grid that the DC microgrid is connected to, right? So that means that AC conventional grid is working at its peak. And if it's doing that, we won't be, I mean, the we won't be able to access much more power required for our system from that grid. So we won't be able to access that kind of power, right? So let's say if it doesn't happen, so we can straight away say, okay, the P car is not there. We can straight away go to the C section. So let's talk about C first. So C checks if our PV is enough to meet the load. If our PV is enough to meet the load, we check if our battery is at its maximum potential, that is 90%. And if it's so, we say that even though just a second, yes. So even though grid we are absorbing power from the grid, what we can do is our battery can be idle or disconnected. Our PV works in a nice point out. So our grid is absorbing, and our battery is in idle or disconnected mode. PV works on MPPT, and our load is basically the full load is supplied. Because since our battery is connected to 89 is 90 degree, we know that our the PV would be sufficient to meet the load, right? So even though grid is absorbing, we just put our batteries to idle because they have reached their maximum potential, and we supply the full load. Let's say the batteries are not charged to 90%. So grid is basically idle or disconnected because we don't need extra amount of power right now because PV is sufficient. Batteries start absorbing, PV works at MPPT, and our load is supplied in full. But if in case PV is not able to meet this load, we check what is the status of our SOC. So checking the status of our SOC is very important because the batteries are crucial for their operation and for effective maintenance. They must not be used at their absolute limit. So that is something that we are checking. So let's say the SOC is not at 60%, it's greater than 60%, then the grid can be idle or disconnected. Our batteries can be supplying, and PV works at MPPT, and our load is supplied in full. Let's say that battery is not at 60%, the grid starts supplying, batteries absorb, PV works at MPPT, and load is supplied in full. So this is something that I would suggest for you to just check everything once by checking this flowchart. You will be able to make sense of it. It's basically an energy management structure where you are trying to optimally utilize all of your resources. So that's the um, that's the basic that's the basic usage of these strategy. And let's talk about their advantages. Haven't So one most advantage is that by properly or optimally utilizing our resources, we can reduce the peak demand that happens in our system. So we can have peak demand reduction, right? We are checking how much of power is available, how much of load we can supply. If not, then load can be switched off, essential load can be supplied. So the power flow control strategy helps in determining the optimal values of these loads. Also, we can have smoother transition between grid connected and isolated mode because since we have a set of strategies in place, we can ensure that a smoother transfer of power happens between the grid connected or isolated mode. Third, since we are following a set of strategies, we can have efficient control and management, right? And since we are optimizing our usage of battery, we can reduce the stress on it. Okay, so this is basically what the power flow control strategy does. I mean, that's the basic um, usage of such a kind of strategy. So, yeah, let's move on. So then the instructor discussed, I mean, some of the aspects of, just a second. I need to discuss some more few aspects. Hmm. So, where did it? Hmm. So, this is one way. Now, the modes that I was talking about, uh, these can be grid connected mode, but in grid connected mode, there are two more modes. That is, if there is a peak hour happening or if there is an off peak, right? So let's talk about these modes. Grid connected. Yeah, so yeah. So we have off peak mode. So that means off peak means our grid has sufficient amount of energy available and we can withdraw that available amount of energy from the conventional grid if required. So conventional, power available. And if the power is available, we can ensure that we can supply the full load. So that's what we were checking, right? So we can either charge our batteries plus supply full load. And one thing it's required is that since you are working on, I mean, you are indirectly working with renewable energy, right? So if you are utilizing the conventional grid more than your requirements, so what are you basically doing? You're basically increasing your carbon footprint. But that's the opposite of what the usage of the DC microgrid was meant to be, right? So you have to make sure that utilization of this grid, utilization of the power available from the grid must not be above a certain requirement, which will increase their carbon footprint. So why does it increase the carbon footprint? It's because the conventional AC grid is assumed to be connected. I mean, it's not assumed. It is connected to the thermal generators or the other non-renewable sources, which can increase the amount of carbon in the atmosphere. So it's indirectly becoming a cause for the increase in carbon footprint, which wasn't meant to be. The second is peak hour mode. So the grid needs energy in this mode, and it doesn't have, I mean, it cannot deliver energy, it needs energy. So you can either supply to grid or disconnect yourself. I mean, disconnect or disconnect or draw minimum requirement. This is only in the case if you have critical loads. So if let's say that your batteries are not charged, PV is the available power from PV is not enough for you to meet the critical loads, you need to uh, take that energy from the grid, right? So that is something that you can do even in peak hour mode, but only for your critical loads, not for charging your batteries or not for supplying of any other non-essential load. And the second mode is isolated mode. So it's pretty self-explanatory. Your conventional grid is absent, and so your conventional grid is absent. And to supply the power, you have two scenarios. So two scenarios. One, the available power from the PV is less than load. What will you do? So if this is the case, your SOC, eh, so you have to be dependent on your SOC. So you check your SOC. Let's say the SOC of the battery is critically low. So any idea what you should do now? So you are unable to have you are unable to withdraw power from your batteries. Your grid is absent. Your PVs are not enough to supply the load. What is one thing that you can do? Anyone who is comfortable with unmuting themselves and talking, I'll appreciate. So what I'm saying is that let's say your PV is the power available from PV is less than what your load requirement is, and your SOC is very critically very low. So what is something that you can do? You can shed some load, right? So load shedding is required. And if the SOC is very high, yeah, we can. Okay. So if the SOC is very high and the available power transfer, but conventional grid is absent, right? So I'm saying there is no other grid present. You have these two scenarios. No, no, no. Multi-grid is something that I'm not talking about. I'm just saying the normal structure is you have a conventional grid connected to your DC microgrid. That's it. So what are the two various reasons possible? Okay, so I'll continue. So let's say that your PV available amount of power from, okay, yeah. If your PV is very greater than your load requirement and your SOC is very high, you can't store that amount of energy anywhere, right? Yeah, yeah, other load should be switched off, yes. So you don't have any power, I mean, you have extra power available. So what will you do? You will operate your PVs at off MPPT. So derate your PVs, don't track the maximum power point. So these are two modes which had different modes in between them that I wanted to discuss before we move further. Next, the instructor discussed the demonstration of the the microgrid. Here he used an RTDS. So this is something that I was telling you from the beginning, right? So these are RTDS racks. Here we have six racks. All of them are synced to the universal time, and these are used to simulate your components in real time, right? That's what we were discussing. The next thing connected to it is this power amplifier. The usage of power amplifier is to simulate the conditions of grid. I mean, it is like a conventional grid for your power hardware in loop simulations. So it can also be used as a DC microgrid. It can be also used as a as an AC microgrid. It has built-in functionalities. So um, this is required, and the last of it, I mean, the things connected here, these are your equipments which are your converters, your conventional loads or something, right? So these are your equipment for, I mean, equipment, I'll just write converters plus loads. This can act as a your DC microgrid, right? So your power amplifier is used for your AC microgrid simulation. This is the RTDS where you do power hardware in loop simulation. So those of you who are not familiar with what RTDS and other things is, I have discussed this in last week, I mean week 9, where I went through some slides where I discussed about these things. So you can always check that. Then to simulate PVs, the instructor used two things. One is a PV emulator. This is a chroma based, I mean, this is a chroma PV emulator, and conventional PVs as well, PV panels. To simulate wind, he used DFIG and a and a diesel generator. So rating, everything is provided by Sir. I mean, it would be unnecessary if I discuss all of that. For batteries, they use these two, the Excite battery and then ultra capacitors for it. So everything is connected to a system and they simulated the whole thing. So they did two kinds of validation. One is controller hardware in loop validation that we discussed, and the power hardware in loop validation. If someone is not familiar with it, I'll again explain. So I think I should explain the original slide. So again, disclaimer, this is something that I've taken from my senior. These slides are not prepared by me. So the credit goes to the maker of these slides, which is Dr. Shesi Som from our institute. So whenever you do, so I'm again explaining it because I want everyone to be on the same page so that once we discuss what kind of simulation happened, this is something that I want you to figure out. So, why is real-time simulation responsible? It's to check if your converter logic or your protection logic will work in real time or not. So, your simulations that are carried out in MATLAB, they are not in real time. So, you could have seen that sometimes when your system is very large, it could take 1 hour to simulate the whole system, right? Or 2 hours to take the whole simulation of the system. This is not something that we want. We want our system to respond in the same manner that we wanted it to behave like. in real time. So that pulses are issued at 5 seconds, that 5 seconds should be in real time, not 5 seconds that the MATLAB suppose time frame the MATLAB uses. So for that, we use real-time simulation that is conducted in RTDS, which is coupled with an RTS card. This is like a MATLAB for RTDS. Here we propose, so this is first thing is software in loop validation, where the control logic or protection logic is in software, converter relay is implemented in software, and your lines and the rest of the network is also implemented in the software. And then you check and validate your system. So once it's done, you move out your converter or protection, your control or protection logic, and then you test out by building this control logic on a DSP board, which is a digital signal processing board, which is then used to issue control signals to your converter or your relay, which is being simulated in the software. So this is called controller hardware in loop, where you remove the controller from your normal setup. The next thing is removing your hardware. So you remove your converter or relay if you're testing a converter or relay, and you check how your system is behaving by connecting your line or other equipment, by making sure that your line or other things are being managed by the RTS CAD only. And once you validate that, the next step is to do a field validation where you implement your logic or your algorithm to a field pilot. So this is something that the instructor conducted, which is called a chill pill experimentation. And to do that, for chill experimentation, they took two case studies. I'll only talk about one because it won't be, I mean, I won't be able to tell you since it's a demonstration, and it's better if you go through that research paper that the sir has posted, Sanjeev Pannala and MP Padhy, Peak Energy Management in DC Microcontrollers. So the controller hardware in loop implementation, they did two case studies. One is power flow control strategies that we just discussed, and the isolated DC microgrid operation. And for power hardware in loop experimentation, they did DC microgrid integration into the IIT Roorkee's network. So, and they coordinated voltage control for the IEEE 33 bus system. The coordinated voltage control scheme we discussed last week. So for the power flow control strategy, the same strategy here. Yeah, this strategy. I mean, uh, similar lines, not same, similar lines. They did for peak mode, off peak mode, and isolated mode. These two are grid connected mode of operations. They simulated it for certain time periods with varying battery status and grid status. So then they checked if, and then they checked how their control strategy was behaving. We'll discuss only one. So for the peak hour mode, they had 5 cases where they checked if the cases are given here, where PV is available in abundance and the battery SOC is greater than 70%. PV is available in abundance, the battery is 70%, less than 70%. PV is not in abundance and the battery is just greater than 30%. PV and batteries are not at optimal power, and in fifth case as well. But the difference between the loads is quite huge. So let's talk about these. I will only discuss one. I mean, this is unnecessary to discuss. I mean, it's already been discussed in the yeah. So, first thing they simulated was case two, in which your PV is generating more power than your load, and your SOC is less than 70%. So, what will you do? Your the T1 is here, right? So you simulated your whole thing, and you see how your uh, the bus voltage is, and what you want to do is in any case your bus voltage should remain at the optimal value, and that is what is happening in any case. The battery is at constant level, and let's say the PV, which is this, your PV is generating power, which is optimal power greater than load, and this is your ultra capacitor. So your ultra capacitor is only used to supply the transients, not used to supply power, only for the transients because it has high power density. And this is your battery status. If it's negative, which is in this case, that is it's charging. Uh, just a second. That is it's yeah, it's charging, and if it's greater than 0, that is it's discharging. And this is your grid conditions, your voltage and grid power. So in case 2, since you have PV available in abundance, what you do, and your SOC is less than 70%, you charge your battery, you supply your load, and your grid is absent. You don't need your grid in this case. And once the case 1 arises where everything is abundance, the SOC is greater than 70%, but so what you will do, your yeah, so your voltage is at constant level, PV is generating, your battery is switched off, capacitor only supports your battery if required, and your UC is not, the ultra capacitor is only used to supply transients, and your load is behaving as it should at 2 kilowatt each. Right. In case 3, your PV is less, but your SOC is there, right? So what you do, your PV is suddenly becomes less, so you start supplying power, and your load is met at full, but you are not taking power from the grid yet. Next case, since your SOC becomes less than 30%, you have to shed your load because you can't make your battery feel critically low. So you shed load, and the load is removed in parts. And this is how it's done. In parts, the load is removed. And in case 4, so this should be case 4. I mean, this is case 5 and this is case 4, sorry. So in case 5, your battery is at less than 10%, so you shed load. And in case 4, since it's less than 30%, you still supply power and you're able to meet your load by supplying power from the grid. So to check all of these cases, I will request you to just go through this and your power flow control strategy. You will be able to appreciate what's happening. All of these are the zoomed versions of your T1 and T5 in time instance. So please go through it and you will be able to appreciate it. Now for field experimentation, the instructor what he did was he took the original Indian power system, which is a huge network of systems. I mean, it's a very huge network. And what he did was he reduced the Indian power system network to a certain level which is manageable and implementable. And out of that, he took out uh, the network for the Uttarakhand state where IIT Roorkee is located. And over there, he checked where the optimal installation of the DC microgrid would be. And why why do we want to reduce our Indian power system network to a lower or a reduced order system? So this is called a reduced order system. So it's very much relevant. It's because the traditional grids are huge. I mean, they are very huge. You have innumerable number of buses, interconnections, branches, nodes, etc. And to model such a grid, it's very difficult. So it's very difficult to model such a grid and find computationally efficient resources to simulate these because these grids are huge, right? In our normal distribution system, what do we test on? It's 33 bus distribution system or 123 bus distribution system, right? But if we check so this is just for transmission. Let's say if we want to check for the whole Indian country, the distribution system will be huge. I mean, too huge to simulate on a simulator. So for that, while preserving the dynamic characteristics of our Indian network, we reduce our system. So this is called a reduced order system. So so reduced order system while preserving the dynamic characteristics reduces the components of a full-blown power system. Right. So basically, you must have checked our Indian network is huge. So we have a total of 2,800 circuit kilometers. So sorry, not 2,800, uh, 28 lakhs. Right. No, 2,08,000. Sorry, I was right. So 280,000 circuit kilometers of transmission network. We have 6,034 buses. So this is a huge bus, right? And we have a net generation. I mean, the net generation currently stands at around how much? I forgot. 220 or 240 or 220 gigawatt. So we have a huge system. So to be able to perfectly balance this system, the Indian power system, I mean, uh, we need to make sure that while preserving our network, we create zones. So since you see that we have a huge network here, we create one zone, two zone, three zone, four zone, and five zone. So we create zones, and these zones correspond to our regional grids as well, right? So we have five regional grids, which are northern grid, southern grid, western grid, eastern grids, and northeastern grids. So these zones are then used to calculate net amount of power available for us, and we then create a reduced order system while preserving the net uh, what do you say net capacity. So in each zone we further have I mean multiple zones. So we created a total 120 zone and 216 lines of system. So this is still huge, but it is still implementable. So coming from 6,034 buses, we reduced it to 120. And then based on these nodes, we check how the instructor checked if his DC microgrid is able to be installed at an optimal location or not. And that's what he did. And my instructor also, so if someone is interested in knowing how the synthesis of this network comes into reality, so there's this paper by my uh, supervisor. It's she what she did was for ERCOT, which is uh, um, Texas ISO. Texas ISO. So for that, what she did was she reduced the system to an 8 bus network. So it's a very good paper, and she has told in detail how the reduction comes into being. I won't discuss because it's not relevant to this material, but if someone wants to discuss it with me, they are always welcome to approach me. So she reduced it to an 8 bus network, and the paper is called, let me check what's the name of it. Okay, it's an ERCOT test system for market design studies. So this paper, she talks about how we can reduce the network, the transmission network, to an 8 bus system, uh, which can be simulated on a normal, um, I mean, a normal system that we have in our or a normal working system, right? So interested people are they can go and check this paper to check how the um, this happens. So, so what the instructor did was he reduced the Indian power system network to 120 zones. So this is still huge. I mean, 120 zones is still huge. So what we have to do is, by reduction, we have to make sure that dynamics and the behavior of the system is completely replicable. I mean, it shouldn't be that I produce a system which is just two bus. So how can the network be simulated properly, right? So this is for the whole Indian network, right? For that 120 bus or 120 zone seems makes sense. So this airport paper, it's for just one state, a simple Texas state. So for that, 8 bus system would make sense. I mean, if you check for Jammu Kashmir, so for that, if you want to make it, will be 4 bus, 5 bus, right? Not more than that. So that is something that you can always do. I mean, so interested people can go through it. It's a very interesting. It's a lot of mathematics to understand, but it's a very interesting method as well, and she has shared the code over GitHub as well for you to try it out if you want to do it for another system app. So feel free. Now, the next thing that we come to is the analysis of AC/DC smart grid. So right now we have discussed a lot on AC grids, DC grids, even hybrid microgrids, or any kind of uh, what you say, um the system that we want to test it out, right? But what really happens is when it comes to the distribution system behaves very differently to the normal, how the normal transmission system behaves, right? This is for distribution system. So why is that? Why is this anomaly happens in distribution system? It's because of two things. One is we have radially connected networks. So, and second, we have high R by X ratio, right? So radially, these can also be connected mesh or loop, but mainly you will see that radiality is prominent. I mean, you will see that the structure goes something like this, right? You have the source bus, then you have the second bus, third bus. In that, you can have multiple buses which are interconnected. This is four, this is five. So this radiality is there, but the system could be meshed or uh, in a loop configuration. So due to this, what really happens is the conventional power flow schemes that we use, right? The power flow analysis, the Newton-Raphson, the Gauss-Seidel, or the fastly coupled load flow, they cannot be employed. So they cannot be employed in our distribution system. So that's what we talked about. This is due to the fact that the power flow at distribution side, which was a Gauss-Seidel, NR or Newton-Raphson, or fast decoupled load flow, right? So all of these methods assumed one thing, that was a low R by X ratio, and that low R by X ratio resulted in coupling between power and frequency, or delta and Q and delta V, right? I should write delta here as well. So this coupling resulted in what you call as uh, uh, due to the low R by X ratio, right? And what we really did was we constructed a Jacobian matrix. So who all remember what the Jacobian matrix is? So it is something like this, J, where we segregated our network into this, where it was partial differentiation of power with respect to delta, then Q with respect to delta, then sorry, right? So this Jacobian, due to low R by X ratio, what really happened was the Jacobian had diagonally dominant elements. So the elements that came in diagonal were dominant. So diagonal, the dominant elements. Why was that? Because of this thing, that coupling occurred between these two things, right? Oh, so coupling happened between these two things. So our matrix was dominant. But now, due to high R by X ratio, this Jacobian will no longer be diagonally dominant. So, and it could be called that it becomes ill conditioned. Yeah. So the Jacobian becomes ill conditioned. That is that they are the Jacobian is no longer diagonal dominant, And ill conditioning refers to the fact that if there is a small variation in input, the output produced from this usage of this matrix would be huge. So if there are errors in if your measurements are erroneous, your result would be largely erroneous, right? So you won't be able to use this because it will be utterly sensitive um, uh, to your small changes in your input values. So for this reason, employment of these power flow schemes could not be used for your distribution system. Right. So now this is one case. So what can you do? I mean, if that's the case, Jacobin is no longer your what you say best friend. So it's unable to be diagonally dominant. It's not able to produce results that you want it to. So what is the other way? It's by simple usage of your KCL KVL algorithms, right? So you can use your KCL KVL algorithms by uh, finding out voltages and then finding out currents and then check if your voltages were correct, and if they were not, then again find out the new values of voltages, currents, till the convergence happens. So you can use your normal KCL KVL or your Kirchhoff's law for the analysis. So this is possible because of the forward backward sweep algorithm. So you can use forward backward sweep for your power fluid distribution side. Now, I'll just give you a brief. I hope you all know about it. I mean, is there anyone who doesn't know what forward backward sweep is? Anyone? Just a raise of hand. Yeah, I think you all must be familiar with it, but still, to make sure that everyone is on the same page, let's say you have a network one, two, and three. You have some load here, and this is your source bus, right? So what you do, you will always use your source bus as your uh, reference bus, right? So you set one angle zero for this. This is one angle zero. The rest of them, you choose any initial value. You can assume a flat voltage profile, or you can just choose any initial values as you would like. So let's say you chose some V2. I'll just write it as V2 bar. It's a complex quantity. And for V3, you chose V3 bar, right? And you had S2, S3, and they were individual line components, right? So now what you do is you check. So it's called forward backward sweep, but first you do a backward sweep. I mean, you just compute your currents in your conductor line. So how you do that? It's by checking what kind of injection of current is there for the load. So I3 is nothing but S3 star upon V3, right? And your I2 will be S2 star upon V2. This is there. So you got your currents by doing a sorry. So you got your currents, right? And your I3 is your I23, that is the current flowing in between these buses, is your I3 only, because there is only one current going through the load. And your I12 is a combination of I2 and I23. So this is your backward sweep. So you performed a backward sweep. Now what you did was you computed voltages. Okay. Yeah. So you compute voltage. How do you do that? You do forward sweep now. Now your forward sweep would check V2 is 1 angle 0 minus Z12 I12, and your V3 is V2 जो भी है यहाँ पे minus Z23 I23. So this was your forward sweep. So this is something that you continue doing till your values converge, and the changes are very minimal. I mean, there's no drastic change between your values. So this is how you do analysis or load flow analysis for your forward backward sweep. So all the other techniques which are distribution flow is also called dist flow, Lin dist flow, etc., are based on these techniques only. I'll appreciate if you go through, if you spend some times and figure out what exactly are the changes between Lindis flow and other things. You will appreciate the whole concept surrounding the power flow analysis for the distribution. Right. So you countered two things. So you countered radiality and you countered the high R by X ratio because you didn't assume that your power flow is decoupled. And due to the radiality, calculation makes it's very easy to do these calculations. So so then this is one kind of an DC distribution network. You can see that we have we have a ring structure here, and we have a radial network. Here is also a ring structure here as well. And the orange side is basically your yeah, orange is your AC side and blue is your DC side. So this is how an AC-DC distribution network looks like. And we should also talk about what kind of buses are there. So types of buses. So you have different types of buses. I mean, these one, two, three are called your buses, right? Or nodes. Bus and nodes are one and the same thing. And so what you do is you name all of them to ease out your calculations. So there are different kinds of buses involved. One is a slack bus. Everyone knows this. You know, everyone knows slack bus, right? What is a slack bus? Anyone? I mean, there are three people online. Okay, so slack bus is is also called, yeah, it's a reference bus which compensates the losses in our system, because what we do is we know the voltage and delta, we set the voltage and delta according to our reference, and we assume that all the losses, all the minor complications that arise due to this power flow analysis are taken care from this slack bus. So your V and delta are known. Then you have PQ bus. So PQ bus is also called load bus. So as the name suggests, you know the P and Q values. So you need to find out V and delta. Then you have, sorry, PV bus. So PV bus is a voltage controlled bus in which you know the value of power, you know the value of voltage, but you don't know Q and delta. So P, so P and P are known. Mostly this PV or voltage controlled bus is used for your to depict if a generator is connected to your system. Because if a generator is connected, your voltage will be regulated. I mean, your voltage will stay constant, right? So this is what a voltage controlled bus is. And then for DC side, you have a P bus. This is for DC. So these were AC, and you have V bus. So this is your DC. So a P bus, you know the value of P. I mean, P is known, and V bus, mod of V is known. And being a DC bus, you don't need Q and delta because there's no reactive power, there's no delta coming into picture. Only needed is the power and the voltage magnitude. So this is something which is completely required for you to do these analysis, because once you know what kind of bus is present, it would be easier to know what kind of unknowns are there, how many unknowns are there, and sorry, how many unknowns are there, and what you exactly require from your system. And to do the power flow analysis, this forward backward sweep on a simulator, so you need to first model this network. Second, model your DGs. Third, model your storages and your converters that are present in your system. So these storages, for storage, so they don't have storage connected. So let's say you need to model your storage, these PVs and your winds. All your DGs need to be modeled as well. So why do I say model? Because you need to know how much power they're giving and how much power they are how much power they're generating or absorbing in any given point of time. Your DJs and the storages I'm talking about. Once you know that, power flow analysis will make sense. So you will see if storage is acting as a load or not, so that you will be able to model it as a load bus or your uh, PV control bus. sorry, a P bus or a V bus because it's a DC source. And all your converters need to be modeled as well. So your converters are basically your devices which modulate your voltage and current, right? So these need to be modeled as well. So like for example here, if a DC-DC converter is there for buck, you know, your E2A will be D times your E1A, which is D is your duty ratio. For boost, it could be 1 upon 1 minus T E1A. And for buck boost, E2A will be D upon 1 minus E1A, right? So this is something that you need to model as well because you want to check how much voltage is being taken out from the converter models as well. So you need to model everything that is present in your system, and then only you can do the power flow analysis. So this is one way, and then you can suitably model each kind of your DG or your converter to suit the need of your system. I want to discuss just a few aspects of your DG modeling. So there are five kinds of DG modeling, four kinds of sorry, type 1, type 2, type 3, and type 4. So if you see type 1, you can only deliver reactive power. Sorry, active power. So these can be your PVs or your fuel cell because they only deliver active power. Then you have devices which can deliver both active deliver active and reactive. So these can be your synchronous machines. They can be made to give both active and reactive power. Then you can have those which can deliver only reactive power. So your compensators are one such thing. Your SVCs, your your compensators are something that deliver only reactive power. And then you have one which can deliver active power but take reactive power. So can anyone tell me what is one device which can deliver active power and absorb reactive power? So we discussed while discussing wind systems. So we are at a stage when our course is culminating, right? So I would appreciate if everyone is able to answer these questions because this is something that we have already talked about, right? So it's an induction generator, right? So induction generator, because it has to develop that rotating magnetic field inside of it, it consumes reactive power while supplying active power. These are some ways you have to model your DGs in these types, and accordingly you can deliver. You can model their buses as PV bus, VDC bus, PQ bus, PDC bus, etc. And the last thing that the instructor discussed today was the architecture of DC microgrid. Again, I won't go into details of how the demonstration took place because all of that component was kind of a video part, which I would ask you to go through that lecture. And so we have discussed a lot about this DC microgrid, right? So it's fairly simple. You have DC loads, you have DC storage, your DC sources, and then you are connected to the grid using a grid connected grid source converter. This is a DC AC converter, and your flow of power is downstream to the grid, and sorry, to the microgrid, and your flow of power is upstream to the conventional grid, and you have different control layers. And uh, on top of the layer, the the dynamics are slow, and at the bottom of it, it's are fast. So at the zero level, you want to control your grid tied inverters variable, then your automatic load sharing and grid support, your macrogrid synchronization, that is V and F control, and your optimization and power flow control at the top of the control layer. So this is the kind of a typical architecture of a DC microgrid, and a DC microgrid is used to support your main grid by uh, by by acting as a grid support where it provides ancillary services. So what are ancillary services? Ancillary services are support services like frequency regulation, regulation, etc. Then scalability, they can add and remove power units seamlessly because you don't require converter stages, right? So any DC kind of source like PV panels, etc., you can directly connect to the DC bus. And these have flexibility, the possibility of reconfiguring the system online during faults by disconnecting from the utility grid. And there is stability because you have sufficient margins between your steady state operating mode and your transient operating mode. So I would request all of you to go through this whole picture where it's given what kind of grid support it provides, harmonic attenuation, etc., etc. So all of them are tied with the grid tied inverter because that is what is used to supply power to that AC conventional grid, right? So using that, you are able to provide the support services from this DC microgrid. So that was all I wanted to discuss in today's lecture. So any questions from today's lecture? I would like to take them now. Then we'll move on to sample problem solving. Any questions? Let me repeat to some of you who weren't present. It would be a brief review of today's lecture. So at first we discussed energy management for a DC microgrid. So this DC microgrid conventional structure is something that we have kept on discussing from like 3 to 4 weeks now. And I discussed about why DC microgrids are becoming prevalent and what are some things that these DC microgrids are. What are some things that are hampering the growth of these DC microgrids? It's mainly the lack of standards and your protection technologies. And then we discussed the power flow control strategy. A power flow control strategy is something that you use to account for your optimal power flow across your network. So you want your components to behave optimally. So for that, you follow a strategy which is like this, in which you keep on checking your resource availability and your other components and their levels so that you are able to devise a normal power flow strategy. So the advantages that are there, it's peak demand reduction. So at peak time, you can switch off your load according to your needs so that it is used to supply only your critical loads. You can have smoother transition between different modes since you are using a float power strategy, right? So you just have to check like if your PV is less than PL and your SOC is at critically low level, you know that you are now you are at the let's say you are at the isolated mode of operation. So you can just check that this mode, okay, I just have to switch off all my non-essential loads and only supply power to the critical load. So this is something that is there if you use a proper control strategy. Third, efficient control. Since you are designing the whole control strategy, you can have an efficient control algorithm across the whole network. And then fourth, you can reduce the stress on battery by properly managing the energy from that coming from this battery. So in the modes of operation, there are two modes: grid connected and isolated mode. In grid connected mode, there is off-peak mode and peak hour mode. In off-peak mode, your conventional AC grid that you're connected to is not experiencing peak power demand. So for that, you know that conventional grid has power available, so you can charge your batteries and you can supply your whole load. And you just have to remember this, that since you are connected to the grid and the power is available, it doesn't mean that you should use that above your requirement. Because if you're doing that, you are increasing your carbon footprint, which is completely irrelevant to the fact that DC microgrids are being developed or these microgrids are being developed to reduce the carbon footprint across the network. And in peak hour mode, you know that your conventional grid is experiencing peak demand. So what you do is you either supply power to the grid if you have abundance, or you only supply critical amount of loads. Then you have isolated mode in which conventional grid is absent. So here two main scenarios are there. Let's say the power from the PV is less than your load. So what you do, and your SOC is at critically low level. So what you do, you shed some load. And if your PV is abundantly available, your battery's SOC is very high, you operate the PV at off MPPT. That is your D rate that PV. Then I discussed a few components that were used for the chill and fill validation of these the control strategies. So I have discussed controller hardware in loop validation in depth. So I would request you to go through my week 10 or week 9 lecture. So for chill experimentation, the instructor took two case studies. One was power flow control strategies and the isolated DC microgrid operation. For chill experimentation, he used DC microgrids integration with the IIT Roorkee's network and coordinated voltage control of IEEE 33 bus system. So I would only discuss case study one because the rest of it is explained by sir. The demonstration is something that is completely, I can't discuss it because I don't know what really happened in that simulation, right? But still, I discussed how the power flow control strategy works. So there are three modes that we discussed: peak mode, off peak mode, and isolated mode. Based on how your battery status is and how your grid status is, you have already devised a strategy and you employ it, and you see that your grid behaves optimally all the time by checking this thing. Your voltage remains at a constant level that you wanted, and your PV battery, your ultra capacitor and load is behaving as it should. In load shedding, your load is being shed. In At times when the SOC is less, your SOC is charging or discharging. This is something that you can check. Then we discussed field experimentation setup. We discussed how the instructor used a reduced order network for the Indian power system and what was its need. So basically, a reduced order system is something that is able to replicate the whole full-blown power system network by making sure that the dynamics are there. The dynamics of the power system operation are present, and that is how they did. They reduced 280,000 circuit kilometers of line connected to 6,034 buses to 120 zones and 216 lines. So this is called a reduced order system. So I also gave you a reference. So this is a reference. This was carried out by my supervisor. She created a reduced order system for Texas ISO, Texas Transmission Network. This is the link of that paper that if someone of you is interested to know how a reduced order system really is made. Basically, what you do is you find hubs of power sources or power generations or where the concentration, or you make sure that you can have the complete dynamic overview of your network by just having that main focus of where your maximum lines are connected or maximum generation is available. And from that, you devise zones. And from that zones, you make your reduced order system. So one thing while making a reduced order system is there that you should be able to replicate the dynamics of your system. The accuracy should always be there. If your reduced order system doesn't behave as it should for a full-blown network, then there's no point in continuing with that um, implementation of the system. Then I discussed the smart analysis or system analysis of AC/DC smart grid, where I discussed how the distribution systems which have high R by X ratio, the normal or conventional power flow analysis techniques such as the Gauss-Seidel, Newton-Raphson, or fast decoupled load flow are no longer relevant because they assume low R by X ratio, which leads to decoupled uh, relevance where delta P is only dependent on delta delta, and your delta Q is only dependent on delta V, which is your voltage magnitude. So what really happens is your Jacobian becomes diagonally dominant, and when you use or employ this for a high R by X ratio network, your Jacobian becomes ill conditioned. That is, your Jacobian is no longer diagonally dependent because then these things also come into being because there is no longer a decoupled situation available. So, so this ill conditioning, what it does is for small differences in your input values, the result produced is very large. So what really happens if you have erroneous values or erroneous measurements, your output becomes erroneous as well, largely erroneous. So we discussed what could be a potential power flow analysis technique is a forward backward sweep, where first you do a backward sweep where you calculate the currents in each of the lines, and then you do a forward sweep by calculating the voltages. You assume that the voltage is having a flat profile. And then I discussed for an AC/DC distribution network what kind of buses are there. Then you have to construct a converter model and DG model for everything because you need to make sure that once you apply it for your power flow analysis technique, how are they behaving in aspects of their power consumption or power delivery. So there are four types of distributed generation modeling. Uh, Pretty self-explanatory. And then I discussed typical architecture. I mean, this has been discussed at length. This in the last video, sir demonstrated a DC microgrid implementation. I would request you to go through it because it's impossible for me to give an overview of that, right? Because it's a video playing where he tells how the different components are connected and what kind of output is being presented over there. So it's better if you watch that video. So any doubts if everyone is on the same page? Any doubts before I continue to sample problem solving session? I listened to your week one video. In that, I seen you talked about 2020 year from RE and Pazu. Can I know the data? What is the source to find generation megawatt from RE? So I don't remember. remember. I just have to check what kind of data was there. This data. This I took from this na powermin.gov.in. Source is given. Oh, right. So yeah. Okay. Any other doubt? Okay. So let's move on to questions this week's. So first question, who will tell me what's the correct answer? So we have two statements. Statement A, a bidirectional DC-DC converter can connect PV panels to conventional three-phase grid. And statement B, ultra capacitors are connected to a DC microgrid using an AC-DC bidirectional converter. Who can tell me what is the correct answer? Easy, right? So you just have to check what kind of source or what kind of component is there. And for a DC microgrid and for a conventional three-phase grid, how should it be connected? It's a fairly easy question, right? Who can answer? A. Statement A is true. Statement B is false. Okay. Anyone else who would like to go on this? Okay, Dharani, I would like you to tell me if there is a conventional three-phase grid, which is an AC grid. So should the PV panels be connected using a bidirectional DC to DC converter? No, right? So statement A is false. We should use an inverter to connect it, right? And then we have statement B. Ultra capacitors are connected to a DC microgrid using an AC-DC bidirectional converter. So we have DC microgrid. This is also DC. So we don't have to use AC-DC. We have to use DC-DC, right? So both statements are false. So question number one, answer is D. Yeah. Second question, we have to select the correct statement. Who can tell me? So we have that AC-DC distribution system is more complex than a pure AC distribution system. AC-DC distribution system has fewer elements. Available load flow methods for transmission systems can also be applied to AC-DC distribution systems. All are correct. So let's start. Available, as I told, no. RBX ratio due to RBX ratio decoupling. This is no longer pure elements. No, we have a large number of elements, converters, then other systems connected to it, right? And yes, AC/DC is more complex than normal AC distribution system. So A is the correct answer. Third, what are the main features of the power flow control strategy in EMS? I mean, AC/DC means hybrid systems. Yes. So AC/DC means both AC and DC components are present in the system. So in a distribution system, this is an AC/DC system, right? That's what we were discussing. It has these panels and these buses in blue are DC buses and these buses in orange are AC buses. Great. So next, what are the main features of the power flow control strategy in EMS, energy management systems? So what does PFCS do? Yes. So we can have peak load reduction, we can have effective control and management, and we can increase the lifespan of our storage system. So all of the above are correct. Second, the transmission losses in the Indian power system as of August 2013 account for dash. Okay. So we have in our system, so losses take place. These are called aggregated ATNC losses, which are aggregated transmission and commercial losses. So these losses are something that happen in the system due to the flow of power, and and they are directly in percentage of the total power generation available in the system. So the correct answer is 2%. So at 2013, the data that they have provided in their lectures, I didn't add that because data doesn't mean anything, right? I don't have to explain you data, right? So 2% of the whole power generation was accounted as transmission losses. So you can see that. So 2% of the system's total power generation, like for example, 200 gigawatt if you take, what is 2% of this? So for 4 gigawatts, right? 4 gigawatts of it was losses. So so your system is your system is inefficient because 2% of it is losses, right? So if you install a 4 gigawatt plant, you can just be rest assured 4 gigawatt of it will be used to supply your losses. That's one way to measure it. So these transmission losses are something that happen in the system. I mean, these cannot be neglected, but it's something that can be worked upon to make sure that these losses could be made a bit fewer than what they are supposed to be. I don't know who's, but US or someplace it's in points. I don't have the correct value. I'll add it if I find it, but there is some place where it's in point digits, right? Fifth, identify the correct statements. So we have fill applications, the control signals. So always remember the control signals are something signals are derived from DSP boards or any other equipment like FGPA or something, right? So these boards are low power devices. So now tell me what is the correct answer. I gave you enough information to answer this question. Yes. So Phil, no. The control signals basically we use boards, right? Plus minus 10 volt. If you use an Arduino could also be used, right? And Arduino has plus minus 5 volts. I don't remember, correct me if I'm wrong, but it has 5 volt um, voltage level, plus minus 5 volt voltage level. But a DSP board could have 10 plus minus 10 volt voltage level. So these are something. So this is true. And complexity circuit will definitely be more in field experimentations because you have converters, relays, etc., which you need to test. So six, what are the different operating modes of PFCS strategy in EMS? Yeah. So we have peak, off peak, isolated. So all of the above is the correct answer. Seventh, what are the five regional power grids in Indian power system? So we have an NLDC, and then we have RLDCs, and then we have SLDCs. So this is the flow of hierarchy between. The answer is A. So this is how the hierarchical control happens in India. The National Load Dispatch Center issues controls or to issues instructions to regional load dispatch centers, which are five, which then send it to the state load dispatch centers, where they are which are there in their jurisdiction. Eighth question: what are the different types of buses in ACDC systems? A. Okay. Anyone else? Yeah. So if you're saying sorry, so you should now tell me the correct answer as well. You know your mistake, right? So you have slack bus, you have PQ, you have PV for AC side, and then for DC side you have P and you have V. So total of five. So let's see. The reference slack bus, PQ bus, PV bus, and DC PQ bus. So PQ bus cannot be for DC, right? It's a DC system. There's no reactive power. So this is wrong. Then you have reference bus, PQ bus, DC PV bus, and DC P bus. So you don't have DC PV bus because you don't have a what you say uh, a voltage control profile which is useful, which you require power generation as well. So because since in a system of AC side you have four different variables, right? You have P, you have Q, you have V, and you have delta. So two must be known at all times to be able to solve the system. So but in DC you have only two unknowns, P and V. So this is something that is not required. Yeah. So the correct answer is D, but let's go through it all. So this is again, this is wrong. Then you have DC bus, PV bus, PQ bus, DC bus. So the correct answer is D. 9. Statement A, it says AC load flow studies refer to the transient state analysis of the power system, computing voltages and angles at each bus. B, AC load flow studies compute voltages and angles at each bus. So, who would tell me the correct answer for this statement? So, so when you say transient state analysis, yeah, yes, B is the correct answer. Let me tell you why. So AC load flow analysis of studies are basically done at a steady state system for a steady state system. That is, you know, your P and Q won't change quickly. Your PQV delta won't change quickly. Yes, 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 yes. And so because in transient state, what happens is your these values could change very quickly, and that is not something that that's not how your computational efficient load flow analysis work, right? So these load flow studies always refer to the steady state system. That is the system which is at steady state, not at a transient state. So answer is that A is false, B is true. Last statement A, the transmission system has a high R by X ratio and the distribution system has a low R by X ratio. So X by R ratio. Who will tell? So X by R ratio. So it's X by R right now for both. D. A and B are false. Okay, why is that? Okay, let's talk about R by X ratio. Let's say R by X ratio. So transmission systems have low R by X, right? And distribution systems have high R by X. That means they have high X by R ratio and they have low X by R ratio, right? So the answer would be C, right? Both A and B are true. So we are just reciprocating, right? If they have low R by X, that means they will have high X by R, 1 upon any value. Right, Dharani? Confusing. Okay. Okay, okay. Let's say that your R by X came out to be 0.01. This is low, right? So if you calculate X by R, which is just the reciprocal of this, which is 1 upon R by X, which is 1 upon 0.01, how much is this? 100. This is high, right? So if you have a low R by X ratio, that means you have a high X by R ratio. So you are just reciprocaling this 1 upon R by X. Yes, yes. Now you got it, right? So the correct answer is C. Both A and B are true. So, so this is something that I wanted to discuss today. So we still have time. If you have questions, I'm here. I mean, you can ask questions. The lectures this week were very, I mean, the material was very less. So I covered everything, I feel. If you want to discuss, let me know. Any questions, anything? Yeah, you can unmute yourself anytime. I mean, if you want to say something or if you want to. Anyone who wants to talk? Nothing from my side, sir. Okay, Dharini. I mean, if there's nothing, you can just leave the meeting. I mean, I'll still be around if you want. Can you say suggestion for how to prepare for exam? Okay. So first of all, I've never given this exam, so I don't know what's really asked. So what I feel is, so everything that's covered. So one thing that I want to clarify, I am a TA for this course from the NPTEL side, not from the instructor side, right? So the instructor side is that TA that gives you the solution of your quizzes and everything, right? So I come from NPTEL side, not from instructor side. So I don't know what kind of questions this instructor would ask because I am not instructor's TA. So, but yeah, best way to cover in a short time is, see my slides. See, I won't say that my slides are very good, but I try and cover everything in my slides. I mean, I give you brief detail of everything. So if you want to have short notes, you can always refer to my slides. These are available in that link, right? But if you want to go through a deeper analysis, I would request you to just go through my slides, see what all is missing. If you want to uh, learn it again, or if you want to check again, go through that instructor's video, and then you can also view my video as well, in which I have covered that lecture. So I would just say there's no best way to prepare for an exam. It's just efficient way to figure out how to prepare for an exam, right? So the syllabus is huge. You can always leave out some part of the system, some part of the syllabus which you don't feel is completely relevant to your to it, which is not completely relevant, like demonstration. So at places the instructor has shown demonstration of various stuff, right? So you don't have to go through that demonstration part. I mean, not the videos of it, but to the major crux that the instructor wants to give you from that demonstration. Like for example, you can always ask these questions. A person can always ask this question. Okay, you have a grid. Your TV is like this. Your load is like this. Your AC, your conventional grid is not connected. It is behaving in an isolated mode. What is the best way to supply power to your non-essential or essential load? So this is something that you have to feel by checking what kind of power flow control strategy could be useful for optimal usage of my components. So you have to come up with that. Like for example, this power flow control strategy. When I explained it to you, it must have seemed to you that it's pretty basic, right? If you have less generation, if you are not connected to the AC grid side, and your batteries are critically low, it always makes sense that you switch off all your loads and only supply to your critical loads. So you have to just see what is developing from this power flow control strategy, right? You don't have to mimic everything. You just have to go through it once and see from your aspect, like if see from your point of view, like you have a battery, right? If your phone's battery is 100%, you will use it, right? But if let's say your phone's battery is at critically very low level, so you'll save it to call in case of emergency. So that is something that you have to, check how you will be able to better answer that question. Coming to how to prepare, just go through all of these questions, go through my slides, go through sir's slides, go through videos if you want to. But slides would be enough if you have covered all of these lectures in a you know in a seamless manner. I mean, I do remember everything that I've covered from week 1 to week 11, right? It's because I went through these lectures, then I prepared my own notes, my own slide deck, and then I gave you the lecture, right? So it seems like I know uh, something of everything from the whole course. I mean, I still won't know everything, but something from everything. So you just go through my lectures, go through my weekly notes, and go through instructors' lectures. You will be able to prepare it in a very short time. Coming to questions are very easy. I feel even the quiz questions were very easy. Last time I took basics fundamentals of electrical engineering from NPTEL side, and questions were tough. I mean, the quiz questions were kind of tough. The students were not able to answer it in one go. They had to be given a push. But this time the questions are very self-explanatory, and there is no zero to no maths involved, right? So you just have to go through important stuff and remember it for the sake of it. I hope I could answer some of your confusion. Yeah. Just go through brief. So I've covered everything briefly. So going through my slide deck, I feel should be enough. Anything else? Any questions from anyone else? I mean, Muttu Selvi, Muhammad Munaf. So I hope you were enjoying my lectures. I mean, it seems like due to less number of people coming to my lecture. I mean, this happened last time as well. There was only one student who came to my lectures for last 5 weeks. I mean, it started off pretty well. There were 20-25 students every day, but then it dropped. And it dropped significantly. I don't know why. People stopped attending lectures altogether. I mean, for other TAs as well. But I hope so. This time attendance dropped, but 5-6 people joined every day. So every week. So I hope teaching was optimal. I mean, I don't know. You have to give me a clear feedback if you found the lectures useful. Due to balancing with job, we are not finding time. So yes, I know. So I also do job, right? My job is to do PhD. So last whole week I was this whole week I was very busy. So I had a few deadlines, and then I had one more TA that I had to complete. So it was all packed for me. So I too have to find time to prepare these slides to give this lecture. So it is hectic, I know, but 2 hours every week I feel is enough for this course. That the 2 hours that you spend on a TA's lecture, it's enough for the course, so that to make sense for you. And okay, yeah, you can always watch recorded videos. I mean, that's why they are posted. Yes, so at least I'm not making any money right now, but if you watch it, hopefully YouTube can pay me as well, right? So yeah. Okay, so if there are no questions from anyone, let's bring this lecture. Yes, let's bring this lecture to a close. So thank you all for joining. Let's meet one last time next week. So let's discuss and let's go through whole course. I feel I'll give you a brief conclusion. I don't know. I have to check if I can give you a whole brief interview. So that's all for this week. I feel. Thank you all for joining. You can log off. You're welcome, Dharini. Yeah, I would request everyone to log off if they don't have anything to say. Please log off, and otherwise, the Zoom meeting will continue unnecessarily.